Well, so it's 5 o'clock and we can start. All right. So can you hear me? Okay. So today's topics. We reached last time Richardson law, and this stated that distance between two particles in turbulence, in fully developed turbulence, will grow as time to the power of 1.5. So x is delta x, distance between them is growing to be proportional to time to the power of 1.5. So with acceleration. Now I also added few photos to the summary sheet. I did not show them during the lectures, but I added them to the summary sheet when you have like smoke traces and nice things like that. And well, this is actually quite important result which you need to keep in mind. Nowadays, for instance, let us see. Nowadays we have that horrible COVID, and people are coughing, and then the virus particles will go into here, and then the question is if you catch them or not. So this is also kind of thing that you need to keep in mind. So the trace of this virus particles will also grow according to the same law with distance. So if you go farther away, you still have a chance of getting it, but the concentration will go down. This also automatically means the result for average concentration. So if we have here like trace going like that, if this distance and the width of this trace is proportional to t to the power of 1.5, then cross-sectional area, which is okay, this is a radius, yeah, radius is proportional to, then radius square is cross-sectional area. This goes to as t cubed, and so a concentration of particles in there will go down inversely proportional to the surface area. So n is inversely proportional to cross-sectional area, which is inversely proportional to t minus q. So actually, probability of pressing in something from there goes inversely proportional to the distance. But then again, if you like walk through it, then you would have like exposure time. If you walk through this trace, okay, and then the overall exposure time is n times time tau, which you spend inside the smoke trace, and then tau is estimated as the width of the trace divided by speed with which you walk, and so this becomes now here on the order of okay, proportional to. So n is inversely proportional to t cubed. So this is t minus 3 multiplied by radius divided by v. Radius is time to the power of 1.5, t to the power of 1.5 divided by v, which is constant. So it is inversely proportional to t, or time is actually distance, the same as distance, minus 1.5. So probability of getting virus, if you walk, you have been told that you need to keep 2 meters distance. So what is magical about 2 meters? Probably nothing. Just the probability of getting infection goes down as a distance to the power of 1.5. That's all there is to it. And if you are far enough, then you say that actually your probability has increased sufficiently, and then it's more or less safe. Well, even safer is just keep in mind wind direction, and if you see someone coughing, then you just go from the other side, and then there is no exposure at all. All right. Now, this is one side of the story when you have tracers like smoke or virus or whatever in turbulence. But on the other hand, now I have shown this picture to you, but I'll be showing it once again. No, okay, now why didn't I? Some connections got loose. All right, so I'll be showing you another picture again. And I take a copy of this thing over here. Something like that. And yeah. Maybe a little too big, but that doesn't matter. So what you have here is now simulation results. Simulation results with tracer, which you imagine as a temperature. So you have a hot wall from the left side, a cold wall from the right side, and then you have an incompressible two-dimensional fluid in between. But what you have in between is the spectrum corresponding to fully developed turbulence corresponding to the Kolmogorov spectrum, which I told you last time, that actually velocity fluctuations associated with a certain scale R go down as a scale to the power 1/3. And now what you have here is temperature distribution, color coded. Yellow is hot, blue is cold. And now what you should pay attention here to is that you have here, you have regions which are regions which are hot. Okay, yeah, here you have hot region and almost no fluctuations. Here you have like something in between, also almost no fluctuations here or here, like flat region. But then you have some regions where you have a very high temperature drop, like you have let us say here, from almost from the hottest to almost to the coldest. Very large temperature drop. And you can find here and there such drops which are perhaps not as big and sharp as over there, but still fairly strong. And so meanwhile, these fronts themselves are fractal, like what I told you before about fractals. If you try to tracing it goes something like that. Okay, it's also a fractal curve. If you consider the front between cold and wall. And so we say that in the case of turbulence, like advection of tracers in fully developed turbulence, you'll be having so-called mature fronts of temperature, well, of scalar, what you have over there. So and yeah, ideally, if you were willing to let the Peclet number go to infinity, like the bachelor scale, where you have mix like diffusion starts to play a role, like small things, temperature differences goes to zero, very small, then you would have a nice picture which is everywhere discontinuous, but just you have like hierarchy of discontinuities. At some points you have very big discontinuities, and in some place you have fairly small ones. A full spectrum of those temperature fronts here. Some of them are big, some of them are smaller, some of them are really tiny, but it's very complicated mathematical object or geometrical object, you would say, what you have here. Also, this is something what you can keep in mind if you go to swimming. Let us say that you swim, and then suddenly you get from cold to hot, or the other way around. And then you know what is happening. You just cross the front, which happened to be there. Now, mathematically, this is like an object which has been described historically using so-called structure function. And structure function, what it is we consider temperature at certain point, and temperature at the other point. So T at R and T at R plus certain A. And then you consider temperature difference T at R minus T at R plus A. And then you take modulus here and to certain power of P, and then you go average. You can average over this full velocity field over R, the reference point R, but then you can also average over different realizations of this thing. And then this is something similar what we did before when I spoke about Hurst exponent. In the case of Hurst exponent, we took P equals 1, and then you said that this difference scales as Hurst exponent. So you remember that if we had a displacement x of t, let us say, and then a minus x at t plus tau, and then we said that if we take this and average, then this goes proportionally to the time delay to the power of h, and this was the Hurst exponent. So what we have, structure function is very similar to that, but it's generalized it. We have power p over that. And now comes a very important concept, which is intermittency. So if our function x of t or t of r, in the case of temperature and coordinate, if this is so-called Gaussian function. Gaussian function means that temperature differences are distributed in a Gaussian manner. So delta t, which is we define as t at certain point. Okay, let us see minus t at 0. Okay, then this quantity here as PDF probability density function as a function of delta r, delta t. A Gaussian one. Okay, because here delta t can be both positive and negative, so basically it means Gaussian function. Then we say that in that case, if like that, then we have Gaussian, then t of r Gaussian function. Gaussian. Now, if we have self-affine Gaussian function, self-affine means that the temperature, the coordinate difference scales as a power law of the time delay. So, if we have self-affine function void, and which is at the same time is Gaussian, then actually this defines everything. And in that case, all these things. All these things that I wrote here, these are actually, there is only one single exponent which describes, if we take the power p, then this exponent just gets multiplied by p. So if we have Gaussian t, if Gaussian, then this structure function is going to scale with distance a as a to the power of h times p. So this scaling exponent is linear function of p. So in general case, this is a to the power of xi, let us denote it xi as a function of p. In general case, we also, in if we have, so to say, multi-affine function. Then we also expect here power law. But the exponent is no longer a linear function of P, and this is non-linear function. Non-linear function in general case. In general case. Non-linear in general case. Now, when do we expect power law? Usually we expect power law. Yes.
You named the intermittency, but I wrote intermittency and I never.
I'm going to those areas. Yeah, still. So it was just introduction. So about intermittency, I still go to speak. So now, when can you expect that that structure function, which is delta t, as a function of a, when we can expect that this is a power law? Well, the answer is if you have no characteristic intermediate scale. Let us say that in the case of turbulence, we have a smallest dissipation scale and we have largest input scale, and there is no characteristic scale in between. And then basically the only function which is so to say scale free, which does not rely on certain characteristic scale, is a power law. Well, it's like it needs to be. It's not always not 100% true, because sometimes you can have something which is almost like power law, but still some considerable, well, asymptotically yes, power law, but in practice it still departs from power law. Like you have things like stretched exponential distributions and things like that. So it's like not absolute, but in general still, if you have no characteristic in between two scales, the smallest and the largest, then you expect a power law. And so that's why in general case we expect over there a power law, and just that if we have Gaussian function, then this power exponent is a linear function of index p, and if it is non-Gaussian, then it may depart from it. And now comes into play intermittency, which actually basically defines that if the statistics is significantly non-Gaussian, which means that you have a significant departure from the scaling exponent h times p from the linear behavior, then we say that this function is intermittent. So if that is in the significant departure from linear behavior, okay. Now, what about the passive scalars? Here, as we saw in the previous graph, we take like what we have in the case of this scaling behavior. We see that if we take delta t, which is very small a, if our exponent psi is positive, and then we would expect actually delta t to go down as a goes down. As the distance a goes down, delta t also is expected to go down as a power law effect. So if we take very small distances, then it should go down. But if we look here, we take very small delta a, let us say in this case from here to here, then a distance between 2 points is very small, but delta t at this point here is big. Well, of course, there are places when delta t is not big. If you take the same 2 points very close to each other, they are almost the same temperature. Delta t is not big, but then in some places it is big. It is big. And now, what does it mean? It means, suppose now that we have like those mature fronts have temperature difference like almost to the largest temperature difference there is. And now let us consider very big p values for the structure function. Like we take delta t to a very big power p and average. Then what does it mean? It means that actually what starts dominating is only the largest temperature drops. Only the mature fronts start playing around. And in that case, we could actually try to figure out what it is. So let us see. Actually, we said that this here is a fractal structure. And now let us imagine that we divide the whole thing into like small boxes, and then count the number of boxes where the fractal structure is. Okay, but this we can relate now to the fractal dimension of it. So let us take next page. So let us try to estimate now, based on this fractal ideology what we have, and let us try to estimate the structure function for a very big P. So P goes to very big, okay, and then delta T to a very big power P and average. So now if we say that there is like there's the biggest delta T, which is almost on the order of the overall temperature drop, but only in very few points where you have fractal, when you have a fractal set for those points of Mathieu-Franz, and then we can say that this is estimated as the number of boxes of Mathieu-Franz. The number of boxes needed to cover the Mathieu-Franz divided by the overall number of boxes what you have there, multiplied by that delta T max what you have to the power of P. Okay, we average delta T to the power of P, but say that because P is very big, the overall contribution is dominated with the largest delta T, is because if delta T is smaller, the value goes very fast down. We can just neglect those where delta T is not taking the maximum value. And then this thing over there, then this thing over there is going to be now depend on the scale A. So we take this at scale A, right? So we need to now take a number of boxes at scale A. So this is proportional to about A to the power of minus d fractal, and here this is A to the power of minus d, the dimensionality of the space. So overall, this is going to be A to the power of d minus df, co-dimension of the Mathieu-Franz multiplied by delta T to the power of P. And now let us recall what was the structure function scaling exponent. Structure function scaling exponent was something which came with A to the power of psi of P. Now let us go back what we have here. So actually this guy over here is going to be actually that psi as a function of P. So I can see here that if we have this if this structure here corresponds to the situation what I was telling, that we have Mathieu-Franz somewhere, and at Mathieu-Franz you have like the biggest possible temperature drop. Then we would have results like that, stating that at the limit of very big P goes to infinity, psi of P would be then to d minus d fractal, which is larger than which is larger than 0. Maybe it's the smaller than the embedding dimensionality. If d fractal actually it can be something like Cantor dust maybe. So, so in that case, d fractal is smaller than 1. So it is something probably between 1 and 2. So psi of P is probably somewhere from 1 to 2. Now, okay, the question is if this picture is true or not. So Sarah Paper actually studies which like believes this to be true. My own result is slightly different, like according to which actually, according to this, what we would have that if p goes to infinity, this psi of p goes to the asymptotic value. Asymptotic value, which is at d minus df. So the question is, if we plot here scaling exponent psi as an index of p against p, then it starts at small values of p, it grows because delta t goes to the power of p. Yeah? So it goes proportionally basically to p, but then here we see that it should like kind of go to asymptotics, but what I have obtained from my model, actually it's going to grow slowly logarithmically. Well, the difference is not really very big for practical cases between those two behaviors, because usually you cannot calculate structure functions for very big values of p. Why you cannot calculate very big values of p? This is because there is not enough statistics. So if you calculate something like so take certain average, and here actually that structure function is delta t to the power of p averaged. Now here what we saw is that the ending results is dominating by those few points of small sparse fractal set. But there are only very small number of points as the fractal point. So statistics for determining that delta t to the power of p, if p is big, is very bad. Only very few points define the final value. And so actually you need to have a lot of data, lot of different ensemble realizations to calculate it reliably. And so actually the sum of rule is that usually you would due to insufficient statistics, it makes sense to keep p smaller or equal than 6. Well, you can go maybe to 7 to 10, but not bigger. Anything bigger than 10 is usually just errors, because there is not enough statistics to calculate really precisely. And that's why in practical OX actually is different between if it's logarithmic or going to asymptotic. In practice, the difference is not really that big. Now, but before we go, what about this initial slope of this curve? Initial slope of this curve. So to that end, we actually have exact value for fully developed turbulence for p equals 2. So we have Obukhov-Korsin. I think it is like 1938 probably and 1941 scaling results, which states that psi of 2 equals to 2/3. And how it comes. It's somewhat similar to actually how we are going to derive the Kolmogorov turbulence spectrum. So we learned that in the case of Kolmogorov turbulence, V associated with scale A is scales as A to the power of 1/3. Now, if we have now passive scalars in turbulence, then what happens is that okay, we have certain characteristics scale like the tracer variation, like consider coarse graining of tracer field. Like we say, the tracer field is coarse grained in a way that you have superposition of a function which varies at scale A plus coarse graining. So n overall is a function of O and T is a sum of n coarse grained at scale A at R and T, and we scale over octaves. So A equals like the smallest scale, the bachelor scale or Kolmogorov scale, lambda, 2 lambda, 4 lambda, and so on. Each next is 2 times bigger than the previous. Then you can say that each of the coarse-grained component is more or less smooth, the same, only single characteristic scale. And then we have a spectral theorem which states that basically the spectrum is transferred to the spectral energy is transferred to the smaller scales. So we say that over a characteristic rotation time, for scale, so during tau, corresponding to scale, which goes to is estimated as the scale divided by the speed associated with that scale. But because VA is proportional to A to 1/3, so tau A is proportional to A to the power of 2/3. 1 minus 1/3 is 2/3. And during the characteristic scale associated with that scale, A goes to A half. You know that it becomes stretched, like in turbulence, blow becomes stretched, it becomes narrower, it goes in Fourier space to smaller scales. A goes to A over 2. And now we have spectral energy is conserved, which means that during that scale tau, we need to have the same spectral flux of that spectral energy for all the components. So we have what needs to be constant is now as the transfer spectral energy divided by the characteristic time. So spectral flux must be equal to constant in stationary case if we have constantly keep input, that's the input scale, and then turbulence going to happen all the time, and the perturbation go to smaller scales constantly. The spectral flux is constant, meaning that n associated with scale A divided by 2 and multiplied by total area gives you that spectral theorem. It must give you the spectral energy associated with that scale. Now this goes now during time tau A to smaller scale. So spectral flux is this guy here divided by tau A. So this is spectral flux. Because during tau A, this goes to smaller scale. And this happens at all the other scales as well. If this were not to be constant, then we would have accumulation of spectral energy at certain scales. So if this is constant, as much as energy comes in, goes out. So this is like the main idea here, and also the main idea how to derive the Kolmogorov law. So this guy here is constant, which means that NA square must be proportional to tau A, which is proportional to A to the power of 2 over 3. But NA square actually is basically what it is. It is just the concentration difference between this point and the point that difference A apart. So actually this actually is exactly, it corresponds to case P over delta T, delta N for P equals to 2. So, and from here we conclude now that psi of 2 equals to that 2/3 which we have over here. Yes?
Maybe it's a silly question, but like here, how can we like interpret the physical meaning of the spectral flux?
Right.
Like, with even like hypothesizing like continuous spectrum, like it's not like referred only to some kind of
okay.
energy,
I'll try to elaborate.
Energy, but like how concentration.
I'll try to elaborate. So we have here axis. Here is spectral energy, and let us say n of k square and divided by k. According to spectral theorem, this nk and sorry, not divided by k, but multiplied by k. Multiplied by k. According to spectral theorem, n k square equal times k, like this is basically what it is. So this is integral of Fourier spectrum from k to 2k, which is on the order of nk square times k. So spectral energy nk square dk from k naught to 2k naught is estimated as, because we assume that nk square doesn't change much, so it's nk square times k. So this is spectral energy. And now we plot that nk square against k. Or we can just substitute here, this guy over here, we can substitute with na square, because according to spectral theorem, this guy here actually is equal to integral over the whole space na square the volume over volume. So this is on the order of characteristic value of na square multiplied by total volume V. So we see that this guy over here, nk square and na square, actually differ only by a constant factor of V. And so we can say also that this what we have vertical axis is actually na square, but then k goes to 1 divided by a, because k and a are reciprocal. And now what happens is that if we have a certain spectrum over there, then due to mixing, this moves to somewhere over here. So it goes from k to 2k during the characteristic time tau of 1 divided by a. At 1 divided by k, sorry, tau a, which is tau corresponding to scale 1 divided by k. This happens during this time. And now, on the other hand, this what was here goes to here now. And see what was here goes to here, so like a cascade. That's why we call it cascade. Everything becomes displaced. And then, so condition of stationarity. We assume that at the equilibrium, we have some stationary profile here. What does it mean is that if this goes to here, so the new height is the same as whole height. But what the condition actually of stationarity means that as much as spectral energy goes in from here, goes out from here. Or at any other point, as much as comes in here must go as much spectral energy goes out here. So how much does energy goes from through this line here? So through this line, this corresponds to a line between k and 2k. So how much energy per unit time? And we know that during this time period, tau a, the full everything what we had here goes over. What we have here, this surface area, let us say, the full energy over here was k and k square, and what was the same as na square with a precision of a constant, and now it came to here. So the total amount of energy, spectral energy, amount of spectral energy of spectral energy, which goes through line k equals to k naught, is estimated as the amount what we had over here, which was just na square. But this happens during tau a. So during each tau A, as much energy goes through. So the energy transfer rate, so the transfer rate is that energy what we have NA squared divided by tau A. And this is exactly what is called spectral flux. So how much energy in spectrum goes through a certain fixed line of gate. That is what spectral flux means. If you had different 2 points here, let us say here and here, then you would have either more spectral energy coming in than going out, which means that you would need to have accumulation of spectral energy in between, so it would not be stationary profile. Because of that, the condition of stationarity is that the spectral flux must be constant. Na squared divided by tau A must be constant. Okay, more or less?
It's hyperbolic behavior.
Sorry?
It's hyperbolic behavior.
Not an hyperbolic, because well, what we have because of that we have Na squared is proportional to tau A. Na squared is tau A. But tau A was, in case of Kolmogorov turbulence, was A to the power of 2/3. So Na squared goes as A to the power of 2/3, a power law, yeah. And then I said that actually this guy over here is the same as structure function corresponding to P equals 2. Because Na squared is like fluctuations, amplitude of Na is amplitude of fluctuations at scale A. So this is the same as basically as delta n at scale A. And then we have delta n at scale A squared. It goes as A to the power of 2/3, which means that structure function corresponding to P equals to 2 is equal to 2/3. So now what we have, let us draw that graph again. Yeah, just if P equals to 1. If P equals to 0. If P equals to 0, then everything is constant. If we take delta n to the power 0, it is unity. Unity is constant, so no scaling at all. So if you try now to plot the graph, xi of P against P, and then let us put here P1, 2, 3, 4, 5. Okay, and then we know that for 2 this is 2/3. For 0, it is 0. Psi P is 0, no scaling at all. And then so the graph should go through those 2 points. And now, depending whether we have a logarithmic or saturation behavior, either way it goes something like that through these points, something like that. Okay. This is how in general case psi of P behaves, which is we already have these. From this, it means that it is very intermittent. So in the case of Gaussian function, it should have been something like that, straight line. Gaussian, this is Gaussian. And this one here is intermittent. And very intermittent, that's that. What does mean? Why do I say very intermittent? So if we say, if we look at the velocity, you can do the same thing for velocity spectrum actually. Velocity differences, how they, if we take velocity differences at scale A to the power of P and average how it scales. And in the case of velocity differences, it's much closer to the straight lines than in the case of scalars. So basic scalars are very intermittent in turbulence. So why is actually the concept of intermittency itself? Why it is important? You know, people usually, and for a long time, have been using Gaussian distributions because it's just very convenient to calculate everything if you have Gaussian, and they know how to do it. But then slowly they learned that actually real life is not Gaussian quite often. And so there are those fat days, but last time
I talked to you about Levy flights, and these play an important role. Like in other words, if you had Gaussian distribution, then you have few samples, like 3 or 5 or 7, and then you can say a lot already with a quite good certainty about the whole population of things. Like you take a certain biological species, say, okay, sample A is 1 kilogram weight, sample B is 1.5, then there is 0.7, then there is 2.3, and then based on that you can calculate average and standard variation. And if it's Gaussian, then that's all you need to have, because Gaussian distribution is characterized completely with mean and standard deviation. But if you have intermittent behaviors, then no, because based on this sample, you don't know how many very big ones you have. Like if you go to fishing, you get one fish which is 1 kilogram and 1.5, and then again 1.5, and then half kilogram. But you cannot be sure. Maybe there is a big guy with 10 kilogram or 20 kilogram. So these are fishes are much more intermittent than like mammals. So usually they have much less variance with one population at least. Then again, if you take a human population, so when I was like a preschool guy, I was reading popular physics and math books, and there was a Russian guy, Perelman, who wrote a book, how it is now in English, titled something like Mathematics Can Be Fun or something like that. For like a wide audience. Have you ever read that? No. Okay. There was a lot of different stories, and one was about a mathematician making bets with other guys around, and then they had like a mathematician was like explaining concept of probability and say that okay. Throwing coin head or tails, 1/2. Now, if you have go to the street and then ask what is the probability that first 10 guys are all men and not women, not without single women amongst them. And then, okay, let us calculate. First guy is probably comes with probability 1/2. And then we take to the power of 10. 1/2 to the power of 10 is around 1 over 1,000, 1,024 more precisely. One case out of 1,024, around 1 per mil, you have probability to have adding all guys. Oh, okay, so that's like not very bad thing, but so let's go on. Let us take 100. What is the probability of having 100 guys being all men? And then, okay, let us calculate. So 1 to 10 was 1 out of 10 was 1 divided by 1,000, but 1 out of 100 is already goes to the another factor of 10 to the power. So it's now 10 to the power of -30 is the probability, right? Around 10 to -30. Now, what is 10 to -30? Now, if you try to estimate, it's really small number. So if you were to try like all your life going walking, the number of seconds in your life is smaller. So actually, during your whole life, you cannot, even during the whole age of universe, you would not be able to, because what is the age of universe? Something like 20 billion, is it? Around that, 15 billion, right? Billion is 10 to 9, right? 10 to 9, 10 to 10, around 10 to 10 is the age of universe. Now, in years. Now, how many seconds in year? 1,000, maybe 10 to 5, 10 to 6, something like that. That's not exactly. Okay, something like 10 to 16, maybe 10 to 16, 10 to 17 seconds, maybe. But that is 10 to -30. So actually, it's way more. You would have a way longer time. Okay, then mathematician was very sure in himself and said, let us make that. About 100 people being all men. I put my bike as a, so if I lose, you will get my bike. And in return, because you are so in favor of position, 1 cent is enough. Or maybe €1. And then they went to street. And then there was a military training, and a big company of men came along the street, and he lost it. So what is the lesson from here?
Mind bias.
Sorry?
Mind bias, always.
Well, actually, the lesson is that real life is very intermittent. If you had Gaussian, no correlation, Gaussian distribution, of course, we would have won that. But the real life, the human society is very intermittent. You have all unexpected events coming in your life. Okay? Yes?
So basically, intermittency, it's like how the probability distribution is squished, or it's like
yeah. So yeah, if you have basically
like the most intermittent thing, it's like a constant line, right?
If the situation is so that you cannot make prediction based on the small set what you have, then it is intermittent. But if it's Gaussian, then you can make a prediction, and then it is not intermittent. So it's like more intermittent if it's even more extreme events can happen.
Okay. Then like if like the Gaussian is really flat and like growing up just a bit and then again really flat, it's very intermittent. And if it's like direct delta, it's zero intermittency. Kind of.
Yeah.
Okay.
So yeah, we can actually there's a lot of also that extinction of the those dinosaurs. Yeah, I know. So what is the distribution of all those? Or maybe dinosaurs are also like volcanic eruptions. So based on what we know, there is like some small eruptions, bigger ones, but actually historically there have been much bigger ones, which humankind has never seen, but actually there are evidence that there have been such, like super volcanoes, which just also that how it was that in US the region, tell me, Yellowstone. Park, I think this has been believed or one of a super volcano a long time ago, a big eruption. And then based on what we have here during historical time recordings, we would say no, there are no such things, but actually there are such things and bigger eruptions. This is also one example of intermittency, for instance. So, and then that the distinction of dinosaurs is the same thing. So, based on our historic recordings, there have been no meteorites big enough to cause anything bad, but historically there have been very big ones. This is another example of intermittency. So, the lesson is yes, that human society and not only human, but actually the world around ourselves in general is very much non-Gaussian. And one of the best examples is actually turbulence. And why is turbulence the best example? Because this is something which you can easily study experimentally or numerically, or numerically not so easily because you have need too much computer resources, but at least experimentally you can study. So the experiments are not that expensive. So that's why turbulence is one of the best examples of intermittency. And yeah, well, you know, the Nobel Prize went to guys who studied introduced the concept of complex systems. And Giorgio Parisi was one of the guys who, together with actually Per Bak, who passed away before getting Nobel Prize, he was these were the guys who introduced the concept of self-organized criticality, that actually physical systems quite often, if they are so-called complex systems, they drive themselves into the state of so-called self-organized criticality, which exactly means that you have like a distribution power laws of extreme events let us say another example of power laws is actually the earthquakes. So you know the Richter scale, right, for earthquakes. So this is, as a matter of fact, this logarithmic scale. So if you increase amplitude of Richter scale by 0.2, each next earthquake actually has 2 times more energy. So again, like once in a century, you have something like Richter scale magnitude, maybe 9.3 or 9.5, something like that. But then there are, if you go to smaller ones, you have less and less and less. And this is also power law, or like frequency of earthquake with certain amplitude. And this is exactly one of the that case of self-organized criticality, because the tectonic plates move, and then tensions are formed, like and the system takes a so-called self-organized critical state, meaning that there are when the plates slip, this is earthquake, and there are bigger slipping and smaller slipping, and consequently bigger earthquakes and smaller ones. Okay, but I think it shouldn't go too deep into complex systems right now, so let us keep it here probably. This itself in itself is very interesting topic, but this would be another course. So right now we have course of turbulence mixing, but that would be the course of complex physics complex systems, which I am not doing. All right. So, but what we have here at hand is a structure function and Gaussian and intermittency. Now, actually, from here comes my suggestion for your next homework. There are different public sources of measurements, in particular sea temperature measurements. I found one of those. You can try looking, maybe you can find some other ones, but let me see. Yes?
Intermittency, you said that the turbulence is very intermittent, right?
Yeah.
Okay, this because like it happens quite often that, for example, like usually the velocity referred to different scales are maybe like one in one direction, one in the other, and in the end are making like a normal size speed, but sometimes happen that many scale speeds are summing in the same direction. So I have like a kind of peak of the speed, like a because of summing of different wavelength.
Mm-hmm.
Is this correct?
Understood your question.
Okay.
Perhaps, please let us repeat once again, and yeah.
And I can draw.
Yeah. Okay. Yeah. Please draw.
Like if I have like this motion in this scale, and I have like another scale like this, and another scale like this, and if we assume that it's continuous spectrum, there are like infinite different scales, and when like perhaps like I don't know, in this point there is this scale that is going in this way, but other scale are going in this way, and then like if I make like the sum, like the integration on the spectrum, then I can get a normal value, like I don't know, something. But like it happens sometimes that all the scales are going in the same direction, then I get like in that point like an asymptote of speed or something like that, and then like this is happening like randomly everywhere, because like there are everywhere like infinite continuum spectrum, and like I get peaks around like random.
Yeah. Okay. So like adding different components in the spectrum. Well, actually, probably no. Adding just if you have each distribution of each of the single component is a Fourier spectrum is Gaussian, then the sum will be also Gaussian. You have central limit theorem, which states that if you add Gaussian events, the result is also has Gaussian distribution. Actually, here actually intermittency comes in the case of turbulence and the scalars in the turbulence from so-called multiplicative cascade. Multiplicative cascade. And let me. So what does it mean? A multiplicative cascade.
It's perhaps easier to explain this in terms of not a passive scalar, but in terms of turbulence itself. So we have a certain vortex, and which is like placed and is formed into, let us say, it goes roughly speaking into two vortices. But this goes in uneven balance. So more energy goes to one. This has more energy than this one here. So it is multiple, and then this one here goes. Each of them goes also into two parts, but one of them has again more than this one here energy. And this is the same thing here. One has more, and the other is less. So, so we started with this here having more energy than that, and then this has the most energy, and this has the least energy. And then during each cascade, the difference is multiplied, because each next is multiplies the energy of the previous one by 1/2, slightly more than 1/2, slightly less than 1/2. Okay, we can do here an exercise to that end. This is like what classically is called multifractal. So if we have on the axis, let us say we have total amount of energy which is spread over the axis, and now this is split into two, and then we have here first half has if this is energy 1, this has 1/2 plus epsilon, and this has 1/2 minus epsilon. And then this goes again to 2 halves. This has here now 1/2 plus epsilon to the power of 2. This one here has 1/2 minus epsilon to the power of 2, and but this one here and this one here has 1/2 plus epsilon multiplied by 1/2 minus epsilon, and so on. Okay, a cascade follows. So now let us see. If we try to write it in binary form, this is 0, 0. This is 0, 1. This is 1, 0, and this is 1, 1 in binary representation. First, second, third, fourth, right? If you look at, if you continue the cascade, actually, what you'll be having is first one goes to the power of numbers zeros in binary representation, and last one goes to the number of unities in the binary representation. And if you go to infinity here in this way, you have like 0, 0, 0, 0 start, and then 1, 1, 1, 1. And now, if you think about the difference, even if epsilon was small, actually, now if you have many cascades, the difference is very big. And so this is called a multiplicated cascade. In each next step, you multiply by something. And if there is slight disbalance, then an ending result is very inhomogeneous. And that's from where intermittency comes into play in the case of turbulence. It's very qualitatively speaking. All right, but then I wanted to give you homework. And the homework is yeah, let me maybe I can share your screen. Okay, this web page here, you can here actually download temperature measurements, let us say somewhere in the middle of ocean. So we can somewhat expect that we have more or less what we want to have over here. Because why? Because we have oceanic motion, and then we have constant forcing temperature. Like if it's in somewhere where you have one side, you have sun is heating, and the other side is
like toward north, it is not that much heating, and then there is like a turbulent flow of seawater in between. Then you would probably have something like what we are having. And then if we go in here further on, so we have here certain measurement points, and okay, we have here, you can take one, maybe, or well, something from somewhere. And then you can select here time period and obtain here temperature profile. And you can go and play with this website download. So what you need to do is they ask you to submit your email, make a request. They ask you to submit your emails, and we'll be sending you, prepare the file and send it to FTP server. And then you can download. Temperature as a function of time, and then you need to also specify the period. So what you need to do is to take it as small, as precise time resolution as possible. Probably not that long time interval is needed, and then I'll write also the link over here in the open board file. Okay, here is the address. From here, you can obtain the temperature time series, and your task would be to calculate the structure functions for certain values of p, like 1, 2, 4, maybe like 1, 2, 3, 4, for instance. And you can check also intermittency. So what you can actually you can take as a measure of intermittency, thing like that, like zeta. Intermittency exponent zeta would go like is 2 times psi of 2 minus psi of 4. So second order structure function scaling exponent times 2 minus 4. So if you have Gaussian, this gives you 0. If it's non-zero, it is intermittent. So find homework. Download t as a function of t from here. And find psi 1, psi 2, psi 4. So basically, you need to average, like what you need to do is you have one time series. So you take T temperature at a certain moment T minus T at T plus tau. Take to the power of modulus and power P, and then average, meaning that now we have only one time series. You don't have more like ensemble. You just average over the starting time t, and then you have something like a sliding average. You slide over t. You have and then you have this structure function s of p, s of t, and then s of tau. Sorry, s of tau, and then you can make log plot, for instance. You can make L and S, and here L and tau, and then if it's straight lines, it's the tangent of the slope. Psi would give you the tangent of the slope. If you have log scale. Is more or less clear what you need to do? Not 100%. Okay, I think the download part is clear, right? Download part is clear. Now you have time series. Now you have time series at hand. Each line has temperature, and each line corresponds to one. Probably say it's not very. It's like one temperature reading maybe per day. It would be better to have more often, but it's one. I guess it's one per day. And then you can take like how much the temperature change during one day, more by modules, and you average over all the data points that you have over there. today minus tomorrow, tomorrow minus after tomorrow, and so on. You find the average by modulus. And this will be your structure functions, first order structure function, S1. Okay. S1 would be average of the first power. S2 would be average square. Your average square of the temperature difference, and so on. And for each index P, you plot log graph, logarithm of structure function against the logarithm of the time delay. So today minus the day before corresponds to tau 1, and then today minus 2 days before corresponds to tau equals 2. Then today minus 4 days ago corresponds to 4. Like it doesn't make sense to like 10 days, 11 days, 12 days delays because it's either way it's going to a logarithmic graph. Then you have a very dense population somewhere. So by a factor of 2 or a factor of square root of 2 would be fine. So maybe you can take time delays 1, 2, 3, 4, but then you can skip 5, maybe take 6, 8, and you can start skipping the delays. Of course, you can take all as well, but then it's more handwork. It probably would be easier if you write Python script, but actually you can do it also in Excel or spreadsheet calculation can be also. Just more handwork, but less coding. It's up to you. Whether you prefer doing it by Python coding or by handwork in spreadsheet. Now, do you think you can do it? Hopefully. All right. Just to get the feeling of it. Okay. Now, actually, an explanation why I can also. I have a paper from a long time ago. I can use actually figures from there. It's like less, maybe more convenient. So let me see. I have here something. No. Oh, here. Okay. There it is. And here is like actually when I draw here, I can also take here like plot for a structure function scaling exponents from different experiments and simulations. I previously did just hand drawing, but I can here show you. Let me take a copy paste from here and then paste into the whiteboard. Like that.
Can we have that article?
Yeah, this actually, in that sense, it's a new journal of physics. It's a good journal that you don't really need to have subscription, like free access. And I can also write this. But actually, I wanted to take from here. Here another thing I wanted to take from here a graph explaining from where comes actually why do we have those material fronts and why it is intermittent in the case of passive scalars. Okay, so you get something like that here. So imagine, let me copy the open board and then comment on it. Okay. So imagine we have the first screen here. At the beginning, we have a cold wall and hot wall, cold temp and hot temp. Then we have all the turbulent flowing liquid. And then we have here and there vortices. And at first we consider only the largest vortices, because the largest vortices are the ones which can transport things to a large distance. Smaller vortices are faster, but they cannot transport far away, just keep at the place. So vortex brings some from somewhere and brings to somewhere else. And here somewhere can happen the other way around. So suppose after a certain time we have temperature profiles like that here and like that here. So you see that at certain points they became close. Oops, what happened? And then, but now they are already close. Now the distance is bigger. Now let us consider the effect of smaller vortices. Now the smaller vortices, which are like the next generation, brings them again at certain points closer, and sometimes they bring farther away. And then they can next generation have even smaller vortices, and the same thing happens. And now, actually, from each figure to the next one is a geometric progression in time. So if this is one time unit from first to second, we know that time scale scales as tau is proportional to scale to the power of 2/3. So if we have scale factor 2, then if this is tau equals to 1, then here is tau equals, and this is distance. Now next generation of vortices is, sorry, yeah, it's already written here. Actually, this guy, sorry. It's already written over here, actually, what I was going to write. So if from first to second is time scale 1, then we have next generation. And now actually here, in this paper, I had more general case, not only Kolmogorov turbulence, but arbitrary scaling experiment. Actually, what we have here is psi is 4/3. So here we have tau is around 2 to the power of minus 2/3, because it goes like a scale to the power of 2/3. And if we had scale from here to here, vortice of scale unity, and here we have vortice of scale 1/2, then 1/2 goes to the power of 2/3, which makes it 2 to the power of minus 2/3. And next one is from here to here, we have tau is already to 2 to the power of minus 4/3, and so on. You have geometric progression. And if you continue this to infinity, then the sum of the times will be also finite, because you know that the infinite geometric progression converges. So what you'll be seeing is that actually 2 points can be brought into contact in finite time, because the sum of geometric progression is finite. And then 2 points which were far away were brought to contact in a finite time. And that's why you have those mature fronts, almost like mature fronts. There are always points which have been brought in contact because they just happen to be there. The vortices brings them closer and closer and closer each next generation. Okay, but as you can see, this happens only in a very few points. And yeah, here is like the graph above is structure function scaling in the case of from numerical simulations, and this curve here is my like analytical conjecture, which is the logarithmic curve. Yes.
Maybe it's my impression, but like, why the black side is like more fractal than the white one? Like at the beginning,
just if you see some difference, it's just coincidence. Should be just it was hand drawing, like qualitatively described. I probably was
hand drawing is not a simulation. Okay.
Yes, it's just hand drawing.
Okay.
Like so they explain qualitatively why.
Yeah, got it.
It's like explaining concept and not doing the real precise simulation. All right. So, I think we are almost covered most important results for traces in turbulence, and we can go on. So, what we had? We had passive scalars in small velocity fields. Remember those stripe patterns that we had? Like we had blobs and very dense population of stripes, which says that we have long normal stretching, and then we had like very homogeneous as well. Then we had passive scalars and compressible flows, in which case, depending on compressibility, particles can start gathering into patches. And then we have this case, which is like it's a very classical example of intermittency, in which case we have mature fronts and regions with almost constant tracer concentration, and which are quite often characterized in terms of structure functions. And then we have the Richardson laws. These are like the main important things to describe passive scalars and turbulence. And yeah, of course, before that we had also passive scalars in the case of stationary flows when percolation came into play and things like that. And yeah, we are now more or less ready to go to the next topic. But before we go, do you have any questions to this part?
Temperature isn't very passive.
Well, depending on how big the temperature differences are and what fluid you have. It depends on the bulk modulus, thermal expansion bulk modulus. If bulk modulus is very big, so you give temperature, it becomes moving up, then you can say it's not so much passive. It starts affecting. But even then, if you have fluid, actually bulk modulus is usually not that big. So usually, and depending how violent, so what you need to compare it with is how violent the flow is beforehand. So you need to compare basically two things: force per volume, buoyancy force, then volume. Let me write here. What you need to compare is to see if temperature is passive scalar or not. So on the one hand, force per volume. Force per volume. Let us make it like is now delta rho density difference multiplied by g, right? Multiplied by m, we get multiply v, delta rho v is like a mass of the water, expelled water, and times g is force. Okay, this is buoyancy force per volume. And now, if this is much smaller than, now what? What do we need to compare it with? Basically, with the force due to acceleration of the mass. So you have violent motion of turbulence, or maybe not so violent, but either a motion. So force gives basically, we can also write down Stokes, I guess, which goes like rho d full derivative dv over dt, which is rho d over dt plus v gradient of t, something like that, and this equals delta p gradient of pressure. Yeah, plus gradient p equal to this, something like that. Neglecting viscosity. So what we need to compare with now is additional force here. So actually now we need to add here force per volume because this is all per volume. If you multiply by volume, rho times v gives mass. Then it would be right hand side would be mass. So multiplied by we add here this force per volume density difference multiplied by g. So in order to be able to neglect this term over here, this must be much smaller than those terms over there, than a system over there. And then this term over here is on the order of rho v square and divided by characteristic scale, what we're speaking with. So now things start depending on which characteristic scale you consider, because gradient gives us characteristic scale, right? The gradient phi is fluctuation of v divided by scale at which it happens. So now if this here is much bigger than delta rho g, then we have then neglect buoyancy. And you can also write it like delta rho divided by rho must be much smaller than g divided by v square. So it depends on v square. If you have a fast motion, strong turbulence, then it doesn't matter. You can just safely neglect the buoyancy. Quite usually you can neglect. Buoyancy says that temperature is passive, meaning that temperature differences, they could change the pressure and give rise to buoyancy force, but usually in the cases at least strong turbulence is negligible. Okay. Now, we have still some time today. We can start half an hour, so brief introduction maybe to a brief introduction to turbulence itself. But before going to Navier-Stokes, I would rather start from magnetohydrodynamics. And from magnetohydrodynamics, and so let us write down some Maxwell equations now and things like that. Find this here. So what we have in the case of magnetodynamics is that if there is electric field or magnetic field and the, like conducting fluid moves, then this will give rise to currents. And then we have an electrical current, then there is Ampere's force which acts on the fluid. So let us see how it can be described. We have Ohm's law in the form J equals, it would be conductivity sigma multiplied by E. But because there is also Lorentz force, this needs to be added. And so we had here V cross B. Where V is the speed, the velocity of the fluid. And now, let us take here curl of it. And so we have curl of J equals sigma curl of E plus sigma. Let us bring sigma to the other side actually. It's like stupid carrying over sigma all the way. 1 divided by sigma plus curl of V cross B. And then what is a curl of J? We have now expression curl of V equals to mu naught J. And in principle, I would have also 1 divided by C square dE over dt. Does it sound like familiar to you? So this is like a Maxwell equation you can say also Ampere circulation theorem in differential form, what I wrote. That's Maxwell equation. And then, but here we have curl of J. So let us see what is curl of J. Curl of J, mu not curl of J, let us keep it that way, is curl of B minus 1 divided by C square and d over dt and curl of E. And then all this thing needs to go over here. Apart from that, we have here curl of E. What are you going to do with curl of E? We have another Maxwell equation to that end. So this guy over here is dB over dt. Okay. And then this guy here we keep as it is. And now let us try bringing things together. I have now dB over dt plus curl of, as is curl of d cross b. And then we have on the other side, as that minus, we can bring also to left-hand side as plus 1 divided by C square, but this again is curl of E, is also dB over dt. Plus 1 divided by C square, d square B over dt square. And the whole thing equal to, now let us see, we have here mu not curl of J, but we were expressing actually for curl, we were substituting for curl of J. So actually we need to divide everything by mu not. If I think it needs to be here. Okay, something like moment. And so all together, what we are still missing here is 1 divided by sigma and mu naught, I guess. Is that right? 1 over sigma is already here. And then if when I substitute curl of J, 1 divided by mu naught will be going to in the right hand terms. And then goes this guy over here. Okay, let me first write it as it is. So this is curl of B. And as for sign, I think I'm afraid I lost somewhere sign. Yes, I did lose sign because curl of E is minus dB over dt. Minus dB over dt. So this guy over here is going to be minus, and then probably I lost again somewhere sign. Oh well, let us check it over. So I take this line from here, and then
on the other hand, I have this equation from here, from where I take curl, and then I obtain this line over here. And now I take from here curl of J and put into here curl of J. And when I do that, then I have 1 divided by mu not going to everywhere, going to here and going to here. Or maybe it should be. I think I'm missing here mu naught should be, since mu naught actually goes away from here. I think I should have here mu naught over here, something like that. So that mu naught goes away, and then I have something like that, and yeah, now I think it's okay. I think it's equation is okay. I just was missing here minus sign here. That's what I was doing. And now this term over here, what is this? Do you know what it is? Anyone? Arthur? Curl of B. What is my B? Okay, curl of B. We just apply vector algebra formulas. We have A cross B cross C is B A C minus C A B. Familiar with this formula? ABC is BAC minus CAB. That's what I'm going to apply. But here we have A and B are nablas. So this thing over here is going to be, first we take this nabla with plus, and the other goes outside, and then the dot product of this and that. So we have a gradient of divergence of B. But divergence of B is 0 due to Maxwell equation. And then remains the other term with minus, which is B and square of nablas. But the square of nablas is Laplace. Okay, that's what it is. So this is Laplacian. And now we can rewrite the whole thing as dB over dt equals. No, yeah, before I go, what about this term? Actually, I would like to drop this term. I can say that just my processes are so slow that this term can be dropped. So we have here speed of light. So basically, if our second term is much bigger than the first term, which happens when V because V C in the denominator actually squared. So this happens. So the first term is bigger than second term as soon as the speed of the process is non-relativistic. So you need to take these terms into account if your conducting fluid moves with speed comparable to the speed of light. Otherwise, you can neglect it. So you're going to drop this term here because this is relativistic term. And then I have dB over dt equals curl, let us make it like a curl of V cross P, and plus 1 divided by sigma mu naught, and Laplacian of P. And so is this now somewhat familiar to you, this equation what we have? If we did not have this term over here, then we would have diffusion equation for B. Okay. And yes, this is what happens actually. This is called skin effect, more or less.
So you ever heard about skin effect? Yes. What does it mean? It means that that if you have alternating magnetic alternating current, then also magnetic field is alternating. And then also the current is super called in skin layer. Yeah. Okay. And actually, how it comes now from this equation? Actually, quite easily. So if you have a conducting material which does not move, then the curl term goes away because V is there. So let me copy this last formula to the next page and let us have a look at it.
The skin effect is the one for which cables are maybe like really small ones, and then they are varnished with
yeah, so due to skin effect, if you have really high frequency currents, then because the current is in the skin layer, actually you can make your wires hollow, because either way current is not going to flow there, but only on the surface layer.
Yeah. Okay.
Okay, here is it.
This happens only at high frequency.
Yeah, high frequency. Oh, you'll be seeing right now. We'll be doing here. So, we have here now. Suppose V equal to 0. Then we have a dB over dt equals 1 divided by sigma mu naught and Laplace of B. Now suppose we have consider some specific situation, like we have a wire, and then there is magnetic field. But for simplicity, let us take 2D. This is like a 3D structure, something. But let us take, instead of that, let us take plane, and then okay, current in J is in our direction. Here we take J is in our direction in half semi-space. Here we have sigma conductivity, and here is vacuum. So here is sigma equals to infinity. Okay, like you have semi-infinite wire here. You understand what I'm saying? Okay, all right, very good. Then if J is in that direction, then magnetic field is in perpendicular direction. Because of the Ampere's law, Ampere's corrections theorem, B is that way. Okay, so we consider now if this is X direction, and then this is a Y direction, then we have equation for By. So we have a d By over dt equals 1 divided by sigma mu naught. But now dependence is on X. So it goes now d square b y over dx square. This is our diffusion equation now. And now, because we have alternating current, then all B change sinusoidal. So we say that actually By is complex amplitude B naught multiplied by e to the power of I omega t. But B naught, actually B naught equals to B naught as a function of X. But everything oscillates sinusoidally in time. And so now we plug in this dependence By into here. And then we obtain time derivative can be taken, because now taking time derivative is just the same as multiplying by I omega. And now we have I omega dB naught. dB naught, sorry, it's just B naught. I think time derivative is just multiplying by I omega. I omega B naught equals 1 divided by sigma mu naught. And second derivative of B naught. And this equation we can solve using characteristic equation. So we have lambda square equals sigma mu naught I and omega. And now comes question: what is square root of I? Lambda is now square root of I. Who can tell me what is square root of I? Big question: what is square root of I? So your first year in university, so you remember still? Who can tell me what is square root of I? No. Arthur, do you remember what is square root of I?
Don't remember exactly, but my guess at the moment would be 1 over square root of 2 times 1 plus 5 or something.
Okay, so actually it's quite easy. And so what we have is in complex plane. If we take square root, I is over here. If we take square root argument, the angle in a complex plane goes to divided by 2. Do you remember? If we take z to the power of n argument of z to the power of n equals to n to the power of argument of z. Because of the property of okay, it's very easy. Z is and modulus to the power of ei phi. So z to the power of n equals to z naught to the power of n ei n phi. You'll see that the angle over there in the exponential form goes to multiplied by n. But here n is 1/2. So this goes to here, and modulus goes remains the same. So modulus, you need the square root of modulus, but modulus in the case of I is just unity, because I modulus of I as a complex number is unity. So this is on a circle at 45 degrees. Here is square root of I. And because of that, square root of I is 1 plus I divided by square root of 2. That's it. So that lambda will become 1 plus I divided by and multiplied by now 1 plus I square root of sigma mu naught omega and divided by 2. Now, what does it mean? And of course, plus minus. Plus minus. And what does it mean? Let's try to write down the solution now. The solution will be okay, let us denote this as this is going to be now having units 1 divided by meter. So this is like something, some length divided by 1 divided by some length. Let us call this skin depth delta. Let this, not this one, but let us introduce delta. Let us introduce delta as, we define the delta as 1 divided by that thing over there, square root of 2 divided by sigma mu naught and omega. Then B is going to be equal to B naught ei omega t, and then goes dependence on x, which is going to be e to the power of I 1 plus I and x divided by delta. And now we have here, we have sinusoidal dependence on x and exponential dependence on x. And all comes with plus minus. Again, sorry, I forgot the plus minus. Okay. No, not that easy to. Okay, I wanted actually to delete, just to delete it. No, plus minus. I wanted to write here plus minus. And now we need to take physical solution here. So of course,
if I'm going to draw now profile, let me again now copy this to the next page because I think that I have more or less exhausted what we have here. Next page. Now I need to keep in mind that the physical reality is actually a real part of it. Now let us this is complex form, but let us keep in mind that physical quantity is a real part of this stuff here. So I take here a real solution, which is going to be B equal B naught cosine omega t. Then e to the power of plus minus x divided by delta, and then goes cosine of actually cosine goes to together with I omega t. Okay, this is equals to b naught e plus minus x divided by delta, and e to the power of I omega t plus minus x divided by delta. So we have actually, I need to write it like that, plus minus x divided by delta. So we have sinusoidal dependence and exponential dependence. And if we make a graph now, of course, it cannot go exponentially increasing. It needs to go exponentially decreasing. So profile into the material is going to be exponential decrease and then a sinusoidal profile here. So profile into the material is going to be like that. So this is B at certain moment of time t as a function of x, by. So you can see that the magnetic field is somewhat skinned in the skin layer. And but if magnetic field is skinned, then current is also skinned because we have J equal to curl of B. J is 1 divided by mu naught and curl of B. So because if there is no B, there is no J. So J is only where there is B, which means that that the electric current is also only in the skin layer. Okay, that's what is called skin effect. So if we have that previous equation, now I again need to copy it once again. Then we had one term which corresponds to the skin effect, and the other term is we need to still figure out what it is. So this here is skin effect. Which means that you have basically diffusion. Diffusion coefficient is at 1 divided by sigma mu naught. And if we have fast processes, which means that the skin depth is small. If we have fast, then skin depth is small. If we go or look here into the formula what we had for D, actually this skin depth delta includes 1 divided by omega, square root of 1 divided by omega, which is like the square root of period. And so a square root of characteristic time. So delta goes down as square root of characteristic time. And so if we have fast processes, so that as the skin depth is very small, we can neglect this term here. Say that actually there is neglect diffusion. And then we have only this part over here. Then dB over dt equals curl of V plus V. And now the question is, what does it mean? Actually, it means very simple thing. We could have actually written down it even without any method.
because what we have here states that magnetic flux is conserved through material contours. And I'm going to motivate it a little more. So what we did, we said that we neglect the diffusion term because we have very small, fast processes, fast enough processes, so we can neglect the basically ohmic dissipation. So that Laplacian B terms comes because of Joule effect, sigma conductivity. 1 divided by sigma is rho, the resistivity. So if the resistivity is small, we can neglect it. If we have perfect conductor, we neglect the skin effect. Fast processes and rho is 1 divided by sigma is small. If we have a good conductor, we can neglect this term over there. And then we have this first term over here. But then you know that the Faraday's induction law that electromotive force along a contour is a change of magnetic flux through that contour. And now if we take a material contour which flows together with the fluid, then this law over there states that the magnetic flux is conserved through that contour, which moves together with the fluid. You understand more or less what I'm saying? Yeah. And we can prove it actually show mathematically. Yes, please.
So, like when we have steady state situation, like current constant, then like the current is flowing into the cable like uniformly because it's like a diffusion process through the inside. But when we invert polarity very frequently, then it pushes basically electrons on order. Like it's that like or
what we have here is actually it's easier things that if we take,
is it for Lorentz?
Faraday's induction law, we take a material contour which moves together with the fluid, and then we calculate the electromotive force through it, which is minus d phi over dt. But because we have perfect conductor, so there can be no electromotive force because that would give rise to infinite current. So this equal to 0 if sigma conductivity is infinity, rho is 0. Then we can say that electromotive force must be 0 because otherwise there would be infinite current. And then we have just phi equals to constant. And so what I was saying is about the equation, what we obtained exactly states that we have, once again, our equation was dB over dt equals curl of V cross B. That was our equation. Now let us see if what I said is true or not. Now let us integrate this guy over here over a contour, arbitrary material contour. And then what we can actually change here is the order of the derivative. So we have here now integral d over dt of integral b and dA. Okay, something like that. And then this arbitrary contour and arbitrary surface drawn on that contour actually. And then this can be in 3D, not necessarily 2D, but 3D. And then right hand side becomes now integral of curl of V cross B and multiplied by dA. But then we have Stokes integral theorem, which states that surface integral of curl is circulation of the vector inside the curl. So due to Stokes, this guy over here is going to be contour integral of V cross B dot dl. But now we have a mixed product over here. Here we can actually change two vectors if we change assign opposite. And now let us rewrite it now as let us swap B and DL.
So this now is going to be integral v cross dl and dot b. Now, what is v cross dl? V now consider a small time interval and multiply left hand side and right hand side by dt. So if I multiply by dt, left hand side becomes differential or like the delta. Let's make it delta. Delta integral of b dA, which is a change of the flux. The left hand side has change of the magnetic flux, so and constant. Right hand side is going to have going to have integral, and now let us combine that delta t with v. But delta t is like displacement of that material line equals to delta r. It's displacement of the material line over there. And so this becomes now displacement of the material line r across dl minus is here, sorry, minus, and then cross dl and dot b. But what I have here is a surface area built on two vectors, delta r and dl. Okay, so if we have contour, so it's changed here to somewhere. This is delta r, and here is dl. And maybe the different colors would have been useful. So here is dl. Okay. Now delta r times dl is then let us make different color. Okay, something like that. So we see that actually what we'll be having is now if we integrate over the whole contour, we'll be having the total area difference, magnetic flux difference, because now we take this surface area dot product with B. So the whole thing together is actually the delta D delta B. If we integrate, we can obtain total change of magnetic flux delta V. Surface area multiplied by B. This is all going to be a total change of magnetic flux. Okay? More or less? Ready?
There is the delta V.
Yeah, sorry. Let me write it again. So this guy over here is delta A. Delta dA, or d delta A, whichever, dA. Surface area vector built on a cross product of two vectors forming a small parallelogram. Cross product is perpendicular to both of them, so this is a proper surface element, is differential, and multiply this by B. Now delta dA dot B is equal to d delta phi, change of magnetic flux. And once we integrate over the whole contour, then we obtain delta phi, and this we obtain once we integrate over the contour.
What's the meaning of the delta dA? Like
because it's a little cumbersome, I agree. Once we integrate, why I kept d delta is because I have here delta and here I have the change of the differential, but differential is going to integrate it. So d is because we still integrate, and delta corresponds to change which we have here. Okay, that's why I kept delta d. What is it?
I'm confused by the meaning of the Laplacian of the delta dA of the.
Oh, sorry. Now it became a little confusing because we have Laplacian and we have delta. Both we can result. But no, we don't have here Laplacian. We have only Laplacian. So all deltas is no Laplacians here, only deltas.
not Laplacian.
Delta what?
Is not Laplace square. Change. You use the delta is used a change of something.
Okay, discrete change.
Change, a discrete change, not infinitesimal change. D is infinitesimal, delta is non-infinitesimal. I could actually, of course, use also in infinitesimal. Maybe it would have been easier to have used here infinitesimal change. For some reason, I took a finite change, not infinitesimal change, but could have taken also infinitesimal. So change of that guy over here, BDA, if I multiply this by dt, or delta t, I multiply this left-hand side by dt, from Taylor expansion, I obtain a change of magnetic flux from the left side. Multiply this equation by the delta t, and I obtain this thing over here, because this time derivative of this multiplied by delta t, I obtain change of that, okay? And on the other hand, I just work with that right-hand side. I apply Stokes theorem, and then multiply, say that, let me now multiply by delta t, v delta t becomes delta r, change of displacement vector. So this element here moves to here. Okay, and so this is dl old, new dl over here. And it covered surface area marked as yellow. Delta r dl is the yellow part. And I have here under integral, we have also the same thing, delta r dl, which is dA. dA multiplied by v is the flux through that yellow part. I integrate over the whole contour and I obtain the total flux change. That's all there is. All right, long story short, this equation here means that magnetic flux through material contours is conserved. Now, what are the consequences of it and what is magnetic dynamo? You'll be learning next time. And by the way, this has also quite a lot to do with the Navier-Stokes, because Navier-Stokes can be also written in a similar form, and we'll be discussing also that later, probably next time. All right.
Mathematical part, yes. At the back, no.
Any questions?
Yeah, actually, yeah, I have like, since this part, I guess it's up to me the first argument that like I can search somewhere else also as a book or something. Like, may you suggest us like a book where to follow those things, because like it's really difficult, and I would say just really turbulent as,
right.
as like it's also difficult to follow like the logic passages between one thing and the other. Then if I can ask some suggestion about it, or if I don't know, like I don't know, like, because I'm really confused from like I understand like the small passages, but I don't see the big picture. It's like lost in the space and time.
Yeah, as I said many times, there is no book which has which is like more like would be easy to follow and have everything what we have here. So the task to have here is to cover most things related to turbulence, because the turbulence is quite big to have many things. Usually you have like book divided to one piece here or one piece there. Like if you take turbulence, you start with Navier-Stokes, go to like instability, boundary layer turbulence, some perturbation method, lot of things, a lot of mass, and then you have only cover small piece of what is a whole picture. So what we are doing here is actually we aim to have like a wide picture on the one side, but then of course as a drawback is that we cannot go too deep into each of them. So we try to get a qualitative understanding of many things which are related to turbulence, and there is no book which has the same way things going. So one book what I recommended was Zinnerberg's book of informal introduction to turbulence, and the reason being that this is a book which does not go too much into mathematical details, because most of the books go very fast into mathematical details. But that book does not cover the turbulent mixing, so that part what I come through as well. And this, like, you can consider only as a supplementary material. The book is supplementary material. It just you can extend the understanding of turbulence using that book over there. And not necessarily to the very end of it, but at least some several first chapter is there. And then, but what we'll be having here are like all the lecture notes, but then again, at the end of the course, we can also try to make summary. Okay, you have what I'm doing usually in my other courses is, okay, let us say we have quantum mechanics or electrodynamics or mechanics or whatever, thermodynamics, and then you have or mathematics, mathematical analysis. And then you have a lot of long course, you have like 6 credit points or more, and you have studied a lot. And do you really need to remember everything? Well, most of students cannot do it, myself in the same way. So, but on the other hand, there are a few things which you still need to keep remembering. And so you need to, at the end of the course, I recommend having a look, what are these few things, what you need to take home and remember basically for the rest of your life. So if I have a student who has gone through quantum mechanics and cannot write me relationship between momentum and wave vectors, and I'm saying that what did he do during the quantum mechanics? Well, actually, studying for quantum mechanics was waste because you don't know that one single thing what you need to actually remember from that. If you're not going to yourself all work into quantum mechanics, and of course you need to know more. But if you're going to work in other fields, it's fine if you forgot how to apply all those perturbation methods and calculate some matrix elements and blah blah blah. That's you had it fine, you understood at that time, but that's not what you need to remember for the rest of your life. What you need to remember is, okay, perhaps nice to have remember what is Schrödinger equation about, what does mean wave function, and then how is related energy and frequency and momentum and wave vector, and also on uncertainty principle. And then if you remember those few things, then it's all fine. We are doing the same thing with this course. So we have gone through all things, and then let us recap it and let's see what were the most important things, what you should remember later. Okay. So I don't want from you to have only just some formal exam or things, but just that you would also able to later on put your knowledge to some use later on.
But like like if one day we have to go in that like in that field, like maybe if we had like a full course but we forgot 90%, then we keep the notes and we can just But if we had like few things, we will remember well those, but we don't know about
so, what about those lecture summaries which I said? That is more or less usable. Lecture summaries. I have been sending you a lecture summary.
Yeah.
So do they feel more or less the purpose?
Yeah, but like the problem is that like the blackboards like that doesn't follow the logical order.
Like,
there is no like time arrow.
It's a lecture summary. I am adding those. If you look on those, yeah.
And also, if I may ask, I don't want to be like unkind, but like the graphics, like the like sometimes I lose like how letters are written.
Okay.
And since I'm not writing contemporary to the hearing, then like sometimes I just leave like a parenthesis with empty things and.
I try to give that lecture summary so that I fill the gaps that we have, like this formula from there. I can just copy formula and put some text, and then again copy formula, put another text. So I try to keep it like more or less. If you have tried to look at these lecture notes, please tell me if I need to be more detailed or if there are still gaps.
Yeah,
let us try to work with those lecture summaries as a starting point.
yeah, the first 4
Because,
chapters
yeah.
I did like a merging of my notes and your notes,
Mhm.
and yeah, actually I would have preferred to have more details
Yeah, and
inside
the
the.
thing is that currently I don't have time to prepare full-fledged lecture
Yeah.
notes.
Yeah, yeah.
Well, so it is like, but I can do things what I have been doing. Like, Arthur, how you feel about these summaries? Do I need to be more detailed over there? Or?
So for most of the summaries, it's okay, or most parts of the summaries. Sometimes there are things unclear, but those are very peculiar instances.
Right.
And,
You
yeah,
know what?
but
If you go through my lecture summaries, if there is something which is still unclear, please send me an email, but asking me to elaborate, explain more. I try to do it more or less reasonably at the beginning, but if at some places still some places things still remain unclear, please just send me email, page, lecture note number and page, and about, or you can just take a snapshot and send me a snapshot that please explains that in more detail. And then I'll update the summary and send you a new version.
okay.
There's me like strange errors, like can I send you this file?
All right, is there everything for right now? I have some more questions.
Have you been sending the lecture summaries every week?
Yeah.
I haven't.
You haven't received?
I've just received one on the 10th of September. That's one.
Maybe you are not in my somehow it's a list of visitors. I'll check, and if not, then I'll send all the notes all together.
Yes, thank you.
Okay. Anything else? If not, then bye-bye.
Oh, you have the wrong. Okay. And if you can execute them, then because actually I added just like this